Oh, yeah. If you're on the campus, campus Wi-Fi is not the best often. So, but I mean, there's nothing really we can do about that. Anyways, so 7.2 is what I want to discuss today. So while I'm looking through and finding some examples I might want to work, does anyone have questions? Either about anything we've covered so far in chapter 7. Okay. So this is 7.2 continued. So 7.2 is where we're learning these counting methods, and we have these things called combinations and permutations. So just to remind you, a combination looks like this form. So NCR, this is just the notation for it. And it follows this calculation. That's n factorial over r factorial times n minus r factorial. And this is specifically for, I'll say, order is not important. Order is not important. So like that pizza topping example I worked in the video that covers this, the pizza toppings, the order of pizza toppings doesn't matter, right? You can have peppers, onion, mushroom, mushroom, onion, peppers, onion, pepper, mushroom, blah, 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 right? They're all just one combination. And this nice little setup here it's magical in the sense that it's doing all that math for us. It's getting rid of all of the extra double counting and triple counting of things where where we don't want to double count or triple count because order is not important. The other one, a permutation, noted as NPR, little n, capital P, lowercase r. So these are like in the subscript positions of the capital letter. Is just n factorial over n minus r factorial. It doesn't have that extra r factorial in the bottom. And here, this is when we have order is important. So this is like when things are being ranked. If you have 40 people and you want to pick 3 of them, if you want to pick 3 of them and they're just supposed to represent the group and there's no rankings to the 3 positions, then you might use this to find out how many ways there are to pick 3 people from a group where ranking of each position is not important. However, if you want to pick 3 people, but there are 3 positions like president, vice president, and secretary, then each of those combinations is going to be unique. Right, so then that would mean order is important. So you would use this calculation. In fact, I'll just go ahead and work that, the problem I just said. Let's say, number 1, we want to pick 3 people to form a committee from a group of 40 people. Okay, so in this case, order does not matter because it's just a committee. All 3 of the people are like playing the same role as each other. So if I picked 3 of you guys and said, okay, here's a combination. I'm just going to pick 3 of your names. So let's see, just in order that they're coming up here. So if I picked Chastity, Abbott, and Isaac. Oh, did I spell your name wrong? Abbott and Isaac. Okay, if that's just one example of a committee that I could pick. Then if I reorder this, if I scramble everyone again and then I pick again, so I've got the 40 people in front of me and I pick these 3 people and then I say, for whatever reason, I'm going to pick a different group. So I put you 3 back into the group and ask you to shuffle around, and then I pick again and I end up with Abbott. Oh, did I spell your name wrong too? No, I didn't. Yes, I did. 2 A's, not 2 C's. Anyways, and Chastity, if I pick these 3 people again, these are the same. This should not count as a new unique. This should not count as a new unique way to pick 3 people from this group of 40 people. So I can say, since order is not important, these only count, these only count as one unique committee or group, whatever, whatever it might be. In this case, it's a committee. It might be a combination of pizza toppings or a committee, or who knows, it could be anything that we want to pick, right? Okay. So what is going to be the calculation? So this is one of those things that in order to determine whether order is important or not, you have to think, like, it's not like a math thing, right? It's thinking about the real world problem, what's actually happening in this problem. And once you've convinced yourself that order is not important, then you're working with this fact over here, that any combination I pick with these 3 people only counts as 1. So then you think, oh man, the counting is going to get complicated for this then. But it doesn't have to be, because this nice little combination formula takes care of this issue for us. If I know that my group size is 40 and the committee I want to pick has 3 people in it, then I don't need to think. Once I've decided order is not important, then I know I'm going to use this combination formula. And once I've, or sorry, not combination, we call them, oh yeah, this is what we call them, sorry. There's different names for them. I'm trying to make sure I'm using the being consistent with the textbook. So once I've decided order is not important and I'm using this combination formula, I don't need to think too hard about how many different ways are there to organize these 3 people. I don't need to think about that. I just plug in the formula, right? So that's 3 factorial over 40 minus 3 factorial. Okay. In fact, if you're interested, though, if you still are interested in these things intrigue you, I would note, how many ways are there to order 3 people? If I listed out every combination of these 3 names, there would be 6. And what is the extra thing that we're going to end up dividing by in our formula? It's going to be 6. That's no coincidence. That's the magic that's happening with this combination. But we don't need to worry about that because the formula has already been built for us. So now here, recall that we are going to be doing some tricks with factorials. The first thing to do is to go ahead and take that difference inside the parentheses. You deal with the bigger ones first because, remember that this 37 factorial is going to cancel out with most of the 40 factorial, right? So let me show you what I mean here. 40 factorial is equal to 40 times 39 times 38 times 37 times 36, etc., all the way down to 1, all the way down to 1. And 37 factorial is 37 times 36 times 35, etc., all the way down to 1. So there's no need for us to write that all out, because we know that this 37 factorial is going to cancel with all of this stuff, all of the 37 and lower in the 40 factorial. And what's that going to leave us with? It's going to leave us with 40 times 39 times 38. That's all that's going to be left of these two numbers when they're stacked on each other like that. All you're going to have is 40 times 39 times 38. Now, the 3 factorial was just hanging along for the ride, right, while we dealt with the 40 over 37 factorials. So I still need to write that down there. Okay, and then we're going to have 40 times 39 times 38 all over 6. 3 times 2 times 1, which is 3 factorial, that's 6. And then you just pop this into the calculator. I have no idea what it is, so 40 times 39 times 38 is that. I'll write it out like this. 59,280 over 6. And the final answer, dividing by 6, is 9,880. So that was the forming a committee where the positions are not ranked. What if we want to pick 3 people? Let's say we want to pick 3 people from a group the 3 positions are president, vice president, and treasury secretary. Okay, so the last problem was very similar, except that we were just forming a 3-person committee where the positions were not ranked, right? Or they were not distinct. The 3 positions were not distinct. You're either on the committee or you're not, right? But here, these are distinct. These 3 positions are distinct. So if I pick those same 3 names, if I picked these same 3 names, right, and then I said, okay, Chastity is the president, and then Abbott is the, I'll say VP, and then Isaac is the TS for Treasury Secretary. And then I say, I don't like that group for whatever reason. And I put them back in the group and I scramble, and then I pick again, and I get the same 3 people. But this time, first I get Abbott, and then I get Isaac, and then I get Chastity. I would say now Abbott is the president, and Isaac is the VP, and Chastity is the Treasury Secretary. These are unique combinations, right? unlike the last one, where if I picked those same 3 people, I would not count it as a unique new committee. Here, this is a unique new group, right? I may not call it a committee, whatever. It's a new group. These are distinct. So I can say, since order is important, that's the thing to note here, that we have to note that this is a ranking of the 3 positions. Since order is important, these are unique groups, meaning they each count as their own. They each count as their own. But we don't have to think too hard about what that means for the counting of it all, because we know that once order is important, that we're supposed to use this formula. Or we're supposed to fall back on the permutation formula. And that's giving us n factorial over n minus r factorial. And that's going to be, 40 is playing the role of n, and 3 is playing the role of r here. So I have 40 factorial over 40 minus 3 factorial. And that's going to be 40 factorial over 37 factorial, which we've already looked at what the math looks like for those two. We know that we're going to have 40 times 39 times 38. That's it, right? That's it. And then this is giving us 59,000, what was it? 59,280. So, as I pointed out in the video for this stuff, we've already looked at things that we've looked at problems like this from a different point of view. We've looked at problems like this and said, okay, if I want to pick 3 people from a group of 40, I can put like three little lines here and say, well, clearly the the first one, there's 40 people to choose from, but then one person has been chosen, so now there's 39 people to choose from, and then now 2 people have been chosen, so now there's 38 people to choose from. And I know from our work in section 7.1 that if I want to find every combination, I just take the product of these, and I'm getting this number. And that's okay if you know that order is important. So every single one of these groups that I pick is unique. If you know that, then you can also do this method, because that's all a permutation does, right? That's all a permutation does. We've already been doing permutations. But again, as I pointed out in the video, it's nice to group the permutations and combinations problems together, and just to say, if order is important, use this formula. If order is not important, use the other formula. So just for the sake of, like, for the student, that's why it's structured that way. But I just want to make sure that if anyone is following closely and says, I think I could just solve it this way, I don't need this crazy formula, then you're right. That's true, but only when order is important. If order is not important, you can reason your way through it without the combination formula, but I don't suggest it. I suggest that if you know that order is not important, then you fall back on the combination formula. One of the trickiest things I think about this section is knowing knowing whether order or not, knowing whether order matters or not. So that's why I've been pointing out this, using this word ranked. If the positions are ranked, or hang on, hold on a second, I gotta plug in my laptop before it dies. If the positions are ranked, like president, vice president, etc., or as in example 5 in the text, which I know you can't see, but if you go look in your text at example 5, it says how many possible outcomes are there for the top 3 positions of gold, silver, and bronze. So that means, anytime you're talking about winning a race, first, second, third place, gold, silver, bronze, those are ranked positions. So that would be order would matter. Order would matter. Okay. So what do you guys want to do now? Let's see, what else did I assign for? I've already worked through a few problems in the homework section, or rather in the text. Let's look at, just for fun, number 14 in the exercises at the end of the text, or at the end of the section. It says how many 4-digit even whole numbers exist. First thing you should think about is, do I need a complicated counting technique for this? Do I need a permutation or a combination? Do I need a permutation or a combination? And the answer is no, because I'm not picking things from a group. I don't have like a larger group, and I'm not picking things from the group. It's just, that's just not what this problem is, right? Permutations and combinations require that you have a larger group, like a group of 40 people, and you're picking 3 people from the group. This is not that case. We don't have a larger group of numbers, and we're not picking even whole numbers or whatever. It's just a different kind of problem. So how do we solve this? We want 4-digit even whole numbers. Well, it's going to go very similarly to the finding the total possible combinations for a 4-digit PIN code that we've already done. You can represent each position with a a little bar here, a little horizontal line, and you can write the number of possibilities for each choice, for each position rather. So I know there are 10 digits, so the first choice should be 10. And then it doesn't say that I can't repeat, so I can have a 10 again. And then I can have a 10 again, but what would be the last? Any ideas what would the last position be? So this 10 is saying there are 10 possibilities. In the first position. What are those 10 possibilities? 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are the 10 possibilities you have for the first digit. What about the last position? Any ideas? What would be, maybe just if we listed them out first, that might help. What is an option for the last digit?
8.
Yeah, 8. 8. And you're thinking that because it says even, right? So I could say, well, then also 6, and also 4, and also 2, and 0 is technically even as well. So there are 5 possibilities. There are 5 possibilities because we require that this number be even. And being even is something that only deals with the very last digit, right? Being even doesn't have anything to do with these numbers up front. Oh, I've done something wrong. This isn't right yet. It's very close. I didn't think about this. See if think about something's wrong with the first position. Can you guys figure it out? I will tell you. It should be not a 0. Because if my number starts off with a 0, then it's not a 4-digit number. Like, for instance, like the number 0336. This is a 3-digit number. Well, I should say a 3-digit whole number. Because we know that if I wrote this down and said it's a whole number, you would say, well, what the heck is that 0? It's just 336, right? Why are you putting a 0 up front? That doesn't really make sense. That's not how we write whole numbers, right? If it was just a string of digits like in a password or something, it's okay. You can start with 0. It's fine. But if you're talking specifically like in numbers, like whole numbers, then you can't start with a 0 and still call it a 4-digit number. It's a 3-digit number if you start with a 0. So this should not be 10 because 0 is not a possibility. It should be 9. Oh, where am I? Oh, right here. There are 9 possibilities. There we go. And that will give us, so we can say that there are 9 times 10 times 10 times 5 possibilities. And then I'll put a star here and write the answer down here. That's 4,500 would be the solution there. Okay. So these problems like of this type where you're asked for, how many, even or odd numbers exist and the number of digits and whether they're whole numbers or integers or whatever, these, you have to bring a new tool set to this problem, which is understanding what even means, right? Understanding that even just means that the last digit should be even, right? And then the whole number's even. And you also have to bring the tool to this problem of the knowing what a whole number means, right? Which is what I briefly neglected here. So that's an example of knowing, the tool that you need to bring to this is knowing what even means and knowing what a 4-digit whole number should look like. It should not start with a 0. Okay. Well, actually, that's all I got for y'all. You have questions or anything? You want to look at any problems from earlier? Have I given y'all the review questions yet? I don't remember. I'll just type them in here again if I haven't.
You have, but that's okay.
Okay, yeah, I'll do it again. So 7.1, we've got 13, 18, and 22. 7.2, we've got a lot here. And remember that these problems I'm about to put in the chat are just for extra practice. You still need to do the Hogs to earn credit for the homework. These are just extra problems to look at as a review for the exam. You could do all the problems in the back of each section. There's not that many. It's like 48 and 7.2. I don't know. Maybe that does sound like a lot, but some of them are pretty quick. All right. If there are no questions, then you guys are good to go.